Hello students, in this model we will learn today the detail about the fast and slow frequency hopping, mainly with taking two examples, one on the fast frequency hopping, one on the slow frequency hopping. We will start today with non-coherent slow frequency hopping system with MFSK data modulation. In the last module, we have already discussed about the M array FSK data modulation scheme, which will be the basic data modulation for today's system consideration, both for the slow frequency hopping as well as for the fast frequency hopping. In our example, we have considered a 4 FSK data modulation scheme. It means that we have a M array tone and data can be transmitted selecting any one of the M tones and then transmitting over the air. 4 FSK data modulation scheme will allow you to choose 4 different carrier frequencies from a set of M capital M is equal to 4. Any one of those 4 carrier frequency will be able to choose for your data modulation. We are considering this figure 1, where actually any one of those 4 FSK modulation that you are choosing is shown by this 4 smaller groups in each and every hopping portion. This we have considered here that the beat stream that are entering for modulation, they are having the bit duration is equal to T into TCV. Hence, the symbol duration we are having here, if I consider capital M is equal to 4, then we are having the bit duration symbol duration T s is equal to twice of CB. It means what? It means that actually we are having within a symbol 2 bits, and these 2 bits are actually selecting the frequency tone. For example, for 1 1 our selected frequency tone will be small f1 f4. For your 1 0 it will be f3, and hence it will be f2 and f1 for the remaining 2. Another consideration is that the consideration of time, symbol time as well as the hopping time. The symbol time here will be considered as T s, whereas the hopping time will be considered as the T h. There is a nice relation to consider to be a slow frequency hopping system, which is like this. If your symbol duration is less than the hopping time duration, I mean the T s is less than T h, and not only that, T h is having a integer multiple of T s. Capital N into T s is equal to T h, something like that, then only you can consider that there is a slow frequency hopping going on. I mean, within a hopping time you have multiple number of the symbols getting transmitted. Another consideration here is to understand what is the modulation bandwidth. Capital B here is the modulation bandwidth. Modulation bandwidth consideration will come from the consideration of this T s. His T s is my symbol duration. So, the 1 by T s will give me the duration of this frequency of this modulation frequency or tone frequency. This is 1 by T s. And hence, as we are having 4 in such kind of the tones, so your capital B will be is equal to 4 into 1 by T s. In our case, basically it is capital M by T s will be giving you the duration of the modulation bandwidth. There is another understanding, if I am having modulation bandwidth is equal to capital B, and then what is the total spreading bandwidth? I am having several hopping frequencies available in my hand. Last module I explained that in the case of the frequency hopping, we have a wide bandwidth W, which we divide over the multiple channels. These channels here I have shown by this. So, this is capital F1, capital F2, the hopping frequencies. Over the whole bandwidth W, I have divided the total available bandwidth over such and such channels F1, F2, F3, F4, like that. So, count here we are having from F1 to F10, 10 different channels. So, the situation is such that I am having a bit stream coming into and then based on the bit pattern I am constituting the symbol considering 2 bits, and that symbol is choosing the MFSK tone, and each MFSK tone is getting hopped over a selected frequency, over a selected channel, which channel will be selected from the capital F, and that channel will be selected definitely by a set of the PN sequence. So, for example, in my case the hopping is such that the sequence is something like this: F1, F2, let me complete this, F3, F4, this is F5, this is F6. Okay. So, my PN sequence has generated such a way that it has selected first F5. So, sequence was obviously 101, and then the sequence was F1. So, it should be actually that 0 0 1, then it is going to F4. So, it will be 1 0 0, and then again it is going to F6. So, it is 1 1 0. So, the sequence, there is a frequency synthesizer who is continuously generating the sequence, and based on that generated sequence the transmitted tone is getting hopped over. We are continuing in this slide the discussion of the previous one. So, as we have understood that the whole bandwidth will be the multiplication of your capital B, that is the bandwidth of the modulation bandwidth multiplied by number of such stages you are having. So, finally, this W, in our case, as we are having 10 number of the different channel to hop, and per channel we are having 4 different frequencies to choose. Hence, the total bandwidth capital W will be is equal to 40 divided by Ts. How did it arrive? It is something like this. We understand that B is equal to our M by Ts, and such M by Ts, the such B, how many B's we are having here is equal to 10. So, it is 10 into M by Ts. So, hence we are ending up with 40 by Ts is the total bandwidth. Remember, in order to generate the 10 different frequency hop channels, in order to identify that, you need actually 4 bit for one of the 10 synthesizer frequencies. To generate any one of the synthesizer frequency, you need at least 4 bits to generate it. So, there is one set of the bits who is telling you how to generate and what is the specification of the generation for this frequency hopping synthesizer frequencies. Another is the bit sequence that you wish to transmit, who is actually modulating the carrier by MFSK. In our case, to understand the situation, we have considered the hopping within the hopping duration. The symbol duration is chosen such a way that Th by Ts is equal to 2. This is our capital N. That means, we can transmit 2 MFSK symbols within the hopping duration. So, let us understand now the bit sequence is coming like this: 1 1 1 0 0 0 0 0 0 0 1 1 0 0 and 0 1. So, the first symbol is 1 1. So, hence it should choose small f4. It is the MFSK tone that he is choosing is the highest tone, MFSK equal to 4, and then he is trying to choose the hopping bandwidth. hopping frequency, sorry. The hopping frequency will be governed by the incoming bit pattern. So, incoming bit pattern that we have seen earlier, the bit pattern should be such that it was F1, it was F2, this was F3, F4. So, we are first in the channel number 5. So, PN sequence has first generated 101. We have chosen the channel number 5 and our MFSK tone was 4th. Hence, the transmission should go like this. Our next bit here 10, hence the symbol is 10. So, he will choose the carrier MFSK tone number 3, which is equal to my F3, and at that moment PN sequence should not, there is no change in the hopping, because within the hop duration like this, within one hop duration we are allowed to send 2 symbols. So, hence with the same channel PN sequence is not changing its frequency and is not generating another hop frequency. Hence, the second symbol is also getting transmitted in the same channel F5, but only thing is that based on the data, the modulating tone has got changed. Now, after 2 symbol duration in the third slot, when the bit pattern has changed to 00, so the symbol is actually 00, choosing the MFSK tone 1, which is the lowest tone, and at this moment the PN sequence has generated the synthesizer frequency is equal to 001. So, you are choosing channel number 1 and transmitting with the MFSK tone 1. The next beat pattern is again 00. So, again you are transmitting with tone number 1 only. Like that, if you proceed, if you will be able to see that for corresponding for these 2 tones, the tone frequency, synthesizer frequency has not changed, so the channel has not changed. Here the channel has changed, so PN sequence has generated the equivalent number 011, which is choosing the channel number 3. And based on the beat pattern, once you are at frequency MFSK tone number 1 and here you are in the MFSK tone number 4. So, without changing the channel, you are basically changing the tone you have chosen. So, with this understanding, this is the way the MFSK slow frequency hopping system data is generated. And we will quickly have a look into the receiver, where actually we will change the receiver pattern will help us to de-hop the signal first and desynthesize the signal, and we will be able to retrieve our own data bit. So, this is a typical task getting performed in the receiver. In the receiver, de-hopping synthesizer we use to de-hop the incoming signal that first leaves the modulation frequencies. For example, we were hopping over F1 to F2 to F3 say. So, that hopping will be turned off. So, that is the meaning of de-hopping, and they will produce the original data bit sequences. If we are considering that we do not have any noise in the system, then the de-hopping and demodulated channel bits will look like this. See, after this is a modulation bandwidth. We saw in the earlier slide, that first we have transmitted we have transmitted over the channel. So, now the channel, the hopping over the channel concept is over because it was de-hopped. So, now we will concentrate only on the MFSK tones we are left with once the hopping pattern is turned off. So, first we had the highest F4, the frequency tone F4, then we are having the frequency tone F3, then we are having the frequency tone F0 simultaneously for 2 symbol period. So, like that here in the receiver we are getting bit back. First the tone number F1, first we were in the tone number say F4, then we were in the tone number F3, then we were in the tone number F1, it is not 0, it is F1. So, we were in the tone number 4, then we were in the tone number 3, and then we were in the tone number 1. and like that actually we are ending up with the different MFSK modulated received signal, and easily actually we can get our demodulated data back, because we understand that actually the highest frequency MFSK tone corresponds to the data symbols 1 1. So, this is the simplest way to understand the 4 FSK modulation scheme, and we can actually change the modulation from 4 FSK to 8 to 16 and to 32 to complicate the system more, and also we can actually change the hopping channel, available channel bandwidth. You can divide the available bandwidth over from 2 to 4 to 8 to 10 to 16, anything you wish. Example 2, now we will talk about the fast frequency hopping system. With the help of a example only, we will start with once again to make the understanding clear. Remember again, we are starting with a 4 FSK modulation scheme, and remember we are having a 4 hop frequencies. So, my channel, this is equal to my channel I am having 4, F1, F2, F3 and F4, which corresponds to our understanding F1 to F4 like the earlier slide. And here 4 FSK modulation scheme means capital M value is equal to 4. I can choose any one of these frequency tones for my transmission. And but remember, it is a fast frequency hopping. So, the way we will be hopping is the way we will be hopping is something like this. For each and every transmitted signal, for each and every transmitted bit, the hopping will be going on. The thing is, when we will define a hopping to be a fast is or slow is something like this, it is relative to the available hopping duration. If your symbol duration is actually greater than the hopping duration, that means for within a symbol duration there is a change in the channel, you are hopping from one frequency to the next, then this is a really fast hopping. And if it is vice versa, I mean the symbol duration is small compared to the hopping duration what we saw in the last slide, then this is a slow frequency hopping. Here we will see the effect like this, that how actually when the symbol duration is larger than the hopping duration, how the hopping is going on. The appropriate bandwidth for this 4 tone modulation can be written as BWB is equal to 4 by TH. So, what is this? 1 by TH we saw actually earlier, that is the separation between 2 carrier MFSK tones that we have selected. So, this is equal to 1 by TH. This was earlier it was 1 by TS. This time actually it will be governed by, because TH is the lowest possible time duration in our situation. So, here it will be 1 by TH, and we have such 4 different tones to choice. So, it will be 4 by TH in our situation, in our case. And that is the total bandwidth. How will we go ahead with? We have 4 such channels. So, total bandwidth will be 4 into 4 by TH, which is 16 by TH finally. And we will consider that n is equal to 2 like the earlier case, which means what? Which means that we have 2 hops for 4 array modulation tones. I mean this will be, the point will be clear in the next slide. Immediately we will go. So, this is the situation what we were trying to explain in the earlier one. See, this is the hopping time and this is my symbol time. So, what is happening is within one symbol duration you are hopping twice, and this is the bandwidth of our understanding, and this is the total available spread bandwidth, that the expression, corresponding expression is given in the earlier slide. And here the time axis as usual in the it is on the x axis wise. The frequency hopping transmitter is again we are in the MFSK modulation tone. So, the choice will be something like this. Here the way the thing is coming is initially we have transmitted the bit stream like this. Bit stream came as 1 0, then 0 0, then it came 1 1. Okay, so let us first understand for this. 1 0 came for the first TS duration. 1 0, within that we are having 2 bits, and then we have to hop also twice. So, it is by default coming like this. For each and every beat you are hopping, and let us understand how the PN sequence is coming up. The PN sequence came like this. Out of the 4 hopping, you choose the frequency channel number 1 first, and then you go to channel number 3, and then you come to channel number 1 once again, then go to channel number 4. So, PN sequence is generating like 001, 011, 001, 0100, like that continuously it came. So, what will happen when the first beat came? I should be in channel number 1. Okay. But what is the choice of this tone? The choice of the tone will be given by combinedly by this 1 0, the total symbol. So, 1 0 is equivalently to the choice of the tone number 3. Okay. And so, I am considering that 0 0 corresponds to tone number 1. 1 0 is corresponding, 0 1 is corresponding to tone number 2, 1 0 is corresponding to tone number 3. So, I am considering like this. When 0 0 will come, the tone number 1 will be selected. When 0 1 will be coming, tone number 2 will be selected. When 1 0 will be coming, tone number 3 will be selected, and 1 1 1, tone number 4 will be selected. These all tones are the MFSK tones. Okay. So, first 1 0 came, so I chose the tone number 3, but within tone number 3 I have to hop from where to where? I have to hop from channel number 1 to channel number 3. So, what I did, for every 1 beat, and there are 2 hops. So, for 1 beat I can be in 1 channel. So, I have gone to the tone number 3, but channel number 1, this is my channel number 1, this is my channel number 2, channel number 3, channel number 4. So, see, for the first beat the tone was actually 3, tone number was 3, but channel was 1. When the second beat came, tone was 3, but the channel became suddenly 3. So, channel we have changed to 3. Next bit was 0, but for 0 0 we understand that we have to select the MFSK tone 1. So, we selected tone 1, and we tried to see where the channel is. Channel was F1. So, we were here, and when the channel, when the beat came to the 4th one, then it was again 0. That means the same channel, same tone will be there, but the channel suddenly changed to 4. So, for the same tone, keep the same tone, just change the channel. So, channel got changed from here to here, but see, tone has not changed, because tone was selected by the combination of this pair. So, this is the way we do it. It is very hard actually if we do any change hopping within 1 bit duration. Then to track the stuff, sometimes we do it also, but to track the system in such a situation will be really tough, and those systems are really very fast kind of the hopping system. Next, there will be a non-coherent fast frequency hopping systems with MFSK data modulation in the receiver side. In the receiver side, we will be demodulating it. See, this is a frequency axis and this is the time, and we are having the bit duration as well as the, which is equivalent to my TCB also. As we have understood that our bit duration will be is equal to TCB, the incoming bit duration will be is equal to the TB will be equal to the TCB if there is no coding involved. And as we understood that once you remove the hopping, it is dehopped, then automatically you will be ending up with this kind of the situation. You will be all the bits who were actually in the separate channel, they will come down and side by side they will fall like this. So, the way we saw there, and we will be ending up with coming here actually the bit that we will select, this is the third frequency. So, obviously, we will select the decoded bit is equal to 1 0, here the decoded bit will be 0 0, here the decoded bit will be equal to 1 1, here I am ending up with 0 1, like that automatically will come up. So, if we go and look into the non-coherent slow frequency hopping system, the typical mathematical equations. So, we will be seeing that this is A is the amplitude of the signal that you are transmitting, hence the power will be a square. F k is the hopping frequency that you are transmitting. If we consider the DPSK data modulation scheme, then T d is the duration of that data symbol. DPSK is a very common and very preferable modulation scheme for this slow frequency hopping schemes, and TAH is the hopping duration as we have seen. So, VT will be the signal model where actually this is the portion where your DPSK modulation is going on. This is the frequency hopping section, and this is the pulse shape associated with that hopping getting considered. So, for each and every hop we understood that there will be the number of the DPSK channel bits. Those channel bits here will be considered as TH by TD, because TH is the hopping duration and this is my DPSK symbol duration. So, division of that will give me definitely the channel bits per hop I am transmitting. From the equation number 2, if we take only the way the signal is getting transmitted, it will be simply the complex envelope of that Vt, which is nothing but like the last module we have seen that it will be the real part of that whole transmitted signal of the equation 2, which can be further simplified by replacing this e to the power I j term as cos plus sine, and we will be ending up with the equation 5. This is the simplified form of the signal, that is the DPSK data modulated slow frequency hop signal that is transmitted over the air. So, this is the figure that illustrates how we pack the signal before transmitting. So, these are the all the DPSK data bits that will be transmitted, and remember for the DSSS system, so synchronization is a very typical issue. For that we usually send 1 or 2 reference channel bits to identify, to estimate the frequency or the timing offset in the DSSS system, and then we try to align the rest part of the frame bits so that we can really extract our data. Remember, actually once we are adding the reference channel bits, it does not mean that we have to add always a single reference channel bit, we can have a multiple channel bits also added here. And once we are adding that channel bits, hence given this frame, you are losing some part of the frame to transmit the reference channels. So, in terms of the efficiency we are losing somewhere. So, there is a loss of efficiency associated in the transmission, and how many number of the bits you are adding there, based on that your efficiency is calculated. As here it is 1, so n minus 1 by n is the loss of efficiency. If you increase this number from 1 to some higher, so let us it is capital L. So, basically the loss of efficiency will be given by n minus L by capital N. So, it's like the DPSK system, we can also go ahead with a BPSK kind of the data modulation also. The complex envelope of the frequency hopping signal with BPSK data modulation looks similar that of a DPSK one, where actually instead of my modulation time defined by the modulation time defined by the DPSK, we will be defining it by BPSK. The rest of the part looks similar, where this phase phi k information is this phase k is associated with the random phase that we have seen in the last module. This is a random phase associated with the generation process itself, and it is independent actually from hop to hop. similar to the earlier one, that dj that we have added here, like the dpsk, here also this dj are equal likely random variables, and they are having +1 or -1 equally likelihood values. And remember, this xt can be xt can be formed similar with the similar logic that we have followed in the last class, and then by expanding the exponential term, we will be ending up with the simplified form of the BPSK data modulation based slow frequency hopped signal. Here, like the DPSK case, we will be having the number of the channel bits per hop time given by Th by Td. This is actually the BPSK data modulation getting explained in terms of a figure, where this is the total number of the channel bits we are planning to transmit. And here if we are thinking that there is not a selective jamming going on, and then actually all the synchronization bits we usually prefer to transmit at the beginning. But if there is a chance that actually there is a selective jamming going on, then we prefer to distribute the synchronization bits or the channels like this. Here we have distributed into 2 different places of the whole data stream that is going on. So, this sync words fundamentally can be very sufficiently large to produce a reasonable estimate of the phase and timing, but it heavily depends upon the condition of the channel, condition of the jamming situation, and based on which we design the sync words, which is not having any typical conformed length issues. It is heavily dependent on the dynamic environment. And also whenever you, but please remember, whenever you are increasing the length of the sequence, then definitely your efficiency is decreasing, and it will be decreased by a factor of this capital L that is shown here, In the next module, we will have a discussion on the remaining part of the remaining two part of type of the spread spectrum communication systems, what is the time hopping as well as the hybrid.